So my name is Zane Everett, and as I just mentioned, I'm going to talk about artificial neural networks, not cats playing pianos. So I'm a graduate of DeVry University. I went through the game simulation programming track. After that, I went to the University of Georgia to get a master's in artificial intelligence. I'm still technically currently a student, but my thesis is stalled. It's turning into a dissertation. But in the meantime, I've been given the opportunity to write my dissertation while working at a company called Cogent Education. I'm lead software developer for their serious games. So, going through artificial intelligence, what I was really interested in was adaptive AI. And this, for me, came from, or at least it was really described by another person, and it was described through the idea of flow. When people play games, what makes a good game to them? Well, one measure of it is that when we give people a challenge, if they do not have the skills to meet that challenge, they get frustrated. They go, "Rah, I don't want to play this fucking game, it's too hard." If we give them too little challenge to meet their skill, they get bored. So what we want to do is keep them in this very nice, happy medium where we give them an adequate amount of challenge that meets the skill that they have. Some games, Candy Crush does this in the early levels. You get, as you go through the tutorial, you're gradually introduced to new puzzles, new tools to complete those puzzles, and as you go on, it gets gradually more difficult. It's supposed to match your skill, but not everyone gathers skill at the same rates that everyone else does. So one great use for adaptive AI is that for every individual, they will get a unique experience and it will be tailored to them. So that everyone will stay within the state of flow. They will want to play your game. They will want to buy the sequel. So, artificial neural networks is one type of artificial intelligence that allows for this. There are many different things that neural networks are good at. You can see this list here. I find some of it a little bit repetitive. I pulled this straight from a textbook. One cool thing, like classification, pattern matching, pattern completion, and control, they all seem to me to be very similar. What they're doing is looking for patterns in inputs and producing a correct output. As a part of that driving the car, we have patterns that you can see if you take a texture and you break it down, and you can see patterns as the texture is moving. If we talk about a road, if the road is appearing straight, then we want to steer the car straight. If we see patterns where the road is shifting to the left, we want to steer to the left. This is an input-output sequence that neural networks are very good at identifying, even when there's lots of variables involved that are more complex for humans to figure out what is going on. A couple of other things that they're good at: noise removal. So if you have a pattern is known, you've got some problems with it, you can take out interference. Same deal with optimization. So what exactly is a neural network? Neural networks are based on your nervous system. They have inputs, they have structure, they have weights. And you can see on the right of the image here, what we have on the far left of the image is the input layer. And they have all kinds of funky numbers and letters associating which one's what. But the structure of it is that for every node, we are connecting to every other node in the next layer, and so on and so forth. Those connections are modified by a weight, and each node is given an activation function. That's part of the perceptron. Perceptron is an individual node. When all of that is put together, we have a final output. And as you can see in this case, there were multiple inputs, and we also have multiple outputs. You don't necessarily have to have multiple, but this is something that is very unique about this type of algorithm. Most algorithms usually give you one output. This one will give you many. So let's talk about inputs and outputs. What can they be? So this is specifically the image from driving a car. We have a texture and it represents a series of inputs. And in this case, I believe they were done as floats to represent the three values for the colors. A texture is simply read in as an array, and they become the input values. Which I guess they don't show in that grid. You take all of the, how a texture is written. It's really just a full string of information. It's read in as all the inputs. It goes through its neural network, and it comes out with output as about how far left or right to steer the car. What was really neat about this experiment, it was done in the early 80s and the late 80s and early 90s. That was way back when we didn't have much computing power. Now we have a whole lot more computing power, and we can get these types of things to begin to work in real time. So let's talk about some of the structure and the weights. So you can talk about inputs and outputs and hidden units. So the big part here is, does anyone recognize this sequencing? If we check out this grid at the bottom. So the output, we've got 0, 1, 1, 0. If we look at a switchboard, that's an exclusive OR. And that's done with a neural network. It's a very simple neural network. It has two inputs. It has two hidden nodes and a final output. That's one of the typical neural networks that you're taught the basics on. So what we can see is we start with x1. We check out the weights going to the two hidden units. As the input values come in, they are modified by a multiplier, which is represented in this case by the ones. It goes in so that there is an activation function. This activation function is a step one. I'll talk about others in a minute. But basically what it means is if it is past some threshold, then it is registered as a 1. If it is under the threshold, then depending on the algorithm, it's either a 0 or a -1. That's all this is doing. We take all of the inputs from the previous nodes, we sum them together, we test the activation function, that goes through to the next weight. It gets multiplied, and all of the others for the next node are multiplied together, or added together and gone through the activation function. In this case, we get an output that represents an exclusive OR function. Any questions? All right. So let's talk about the individual nodes. These were originally called perceptrons. Don't really know why. Just a fun name to say. But here are the different activation functions that you can have. You can see we've got a linear relationship, so it's just multiplied by some value. You can have an if statement that creates a step function. A ramp function is very similar. It kind of combines the two of linear and step. So that if it's below a certain threshold, it is your minimal. It runs up linearly to a maximal. It is sigmoidal and Gaussian. So to get a neural network to work, you have to train it. Because the weights that you initially give it, the whole point of this is you don't know what the proper function is. So we have to run it through a series of test trials before we can get an approximate solution. The most common method is backpropagation. What it does, it's kind of a hill climbing function that over time you will gradually converge on the correct weights. It works by feeding forward through the neural network to get a solution, It is testing that solution against some kind of error, and then it distributes that error backwards to the nodes based on how far apart they were. This is a very complex algorithm. It could honestly take an hour to go through. What I've included here is a link. Does anyone know the Wi-Fi? Just get on the Wi-Fi for free, quickly.
I think it's BSAV 4302, if I remember correctly.
PSAV.
Yes.
And what was the numbers?
4302.
Well,
Now they redirect you to where you wanted to go.
exactly.
Yeah.
So, you guys give me your business cards. I will send out an email for these slides. You'll have access to this. What this is a very wonderful walkthrough of how the backpropagation function works. It explains it, it's very wordy, but explains it in very concise wording. It goes through different methods of how you can put the backpropagation function into programming algorithms. One by matrix math, one by summation. It's very nice, very concise. So you can go through on your own time and figure out exactly what the backpropagation function does. One interesting pitfall to the backpropagation function is that it will only train the weights for your neural network. And this is an important distinction because sometimes to get the closest approximate function that you want to whatever you're solving, the structure can play an important part in how well the function will solve that. And so if you are just using the backpropagation function to figure out the weights for your neural network, you may have to try different structure setups and train that, and then train another one, and then train another one, and see which one works best. What is coming up as a new favorite method is a process called genetic algorithms. They basically take the idea behind evolution, and you have a population of solutions, and you basically breed them and mutate them until you get a close approximate. What's very interesting about this method is that you're able to train both the weights and the structure at the same time. So, well, this was to explain a little bit better the backpropagation method. I'm going to stand up. Can't help it later. So, with the backpropagation method, as you've fed it forward, you've gotten your results and your answers. You've compared that to some known correct answer, and you figure out the error behind it. And so what you will take is the error in this, and you will see, based on the weights, how much responsibility each node had to contributing to the error. So from this node, you would bring back the amount of error to this one, and this one, and then to find the appropriate error for this one, you would take the weights from this, and this, sum them, and apply it to this one. And then you would be able to gradually modify the weights for the different nodes based on their responsibility for the error. But in order to train your backpropagation cycle, you have to go through several series of training, testing, and validating the error of the neural network. What's typically done is you use about 60% of a large data set that you know the inputs and the outputs to get to do training. We would go through this set. These are the ones that we would be finding the error on. We use a set for testing that allows us to basically, so once we have our neural network weights built, we would apply it on a testing set to see how much more error there is. We can get into a problem called overfitting. So if we train and train and train on a certain data set, the neural network will get really good at that data set. But if you now give it new information, it can be very off, and that's called overfitting to your data. A way to get around this is through cross-validation. What you will do is split up whatever data set that you have into these ratios, and you will do several iterations on the same data set where you use a percentage for testing, a percentage for training, and a percentage for validation, and then you will use a different set within that same for training, testing, and validation. Each one you're using the same data set, you're just changing which entries in the data set apply to which category. For backpropagation, you are able to do this full training, testing, and validation cycle, but it requires that you have a large and known data set. This can be a problem for video games. If we are trying to adapt a neural network to be based on how a player plays, we don't have recorded information about how a player is playing. This is something we're trying to learn as time goes on.
Quantum computing, perhaps, right? I've heard that should actually be a lot more for that sort of thing.
Knowing what the, so you asked if quantum computing would be a way to solve this. Sorry, I have to repeat the question. It also is good to make sure I understood it. So, my knowledge, quantum computing is a method of speeding up these processes of calculation. We still can't predict the future of quantum computing.
How about collecting, perhaps, say, somebody's data throughout their entire life? The idea of quantum computing, is it actually possible?
So we can gather data, and we could, so we would be able to use the backpropagation algorithm in real time, and we would be continually getting a data set from them and then retraining the network and then using it. I can see with quantum computing that could be done and can be done fast enough in real time, but that's not where we're at yet. Typically for backpropagation, you train your network, and that is your network. It's there, it's done, it's not doing anything else ever again except for solving the problem. The other deal is, how do we have an AI play the game against a new player? Yes?
I was just curious, when you were worrying about the problem of overfitting happening, did you ever continuously go through testing about it to find out what precise point that starts to happen?
You can. So you asked, at what point does overfitting begin in the testing, training, validation cycle? As you continue to train your algorithm, you will train it for a certain number of generations or until you reach some kind of stopping criteria. There are methods of testing when overfitting happens, and you just kind of keep in memory, well, this is the last cycle that I had, or the last several hundred cycles that I had. And then you say, well, overfitting happened here, but not here. Let's go back to this set of information. And that is what this training, testing, validation cycle allows you to do. Is if you keep records of it, you'll be able to see when overfitting happens.
So when you reach the point, or the best point you can find out, supposing you were able to get the point exactly when overfitting starts to happen, would the algorithm be able to predict things 100% or near 100% accurately, or would it be something lower than that as a maximum?
So that's great. So where you asked about the ability of prediction for neural networks. A good neural network will be able to get good answer to a solution 90% of the time. This is part of the pitfall with adaptive AI,
So,
just as a category.
so when you say good, you're talking about the point when you don't want to mess with between overfitting and underfitting, you just sort of stop. This good area would be when you start trying to go over and under, that's the 90% point.
So the 90% point that I'm talking about is if we give the neural network some new data and we ask it to solve based on our training, testing, and validation set, when it has stopped its training and we say, yes, this is a good neural network for this problem, if we give it new data, there is a 90% chance that it will, or I'm sorry, a 10% chance, because we don't want it to be that bad, that's worse than random. It has a 10% chance of not doing the right thing, because this is new data that is presented with and it was trained on a different set of data. There could be something that caused this data and this outcome that the neural network wasn't trained on in the training, testing, validation set. And so it has no idea what to do with it. This is part of adaptive AI based on biological processes. Biology does a very good job of getting it right because the bad solutions are weeded out. And that it eventually happens in adaptive AI. But biology has been doing it for billions of years. We have a much shorter space and time in which to do this. Now we can get 90% of the time it will do what is good. And every once in a while you will get something a little strange. Hopefully it's not enough for the user to be able to notice it, because it should be a one-time occurrence, and that will be weeded out eventually. I guess as getting into this, that is the problem with the backpropagation algorithm, is that once it's done, once the neural network has been trained, you usually don't go back and retrain it. Whereas with a genetic algorithm, it's actually very cheap to go back and retrain the network if you just give it one iteration of a genetic algorithm. It's very similar to one generation in biology. We're tweaking it a little bit and seeing where it goes. And since we've had new input, we can retweak it, and it will be very quick. And so we can continue to train in real time with a neural network using a genetic algorithm. And there's the other deal. It will work with new unknown data, and that's what I mean by this. We can have a new set of input come in, but wow, I knew nothing about that before. I did really bad with this. I can retrain, and I can hopefully get better. And so next time the user gives this type of input, I will be ready. Which kind of gets into what we were just talking about. This is the black box dilemma. So with these types of complex algorithms, no one can really tell you what's going on inside. We can, for the backpropagation, we can see the formula, we can know how it works. But how the weights are really being distributed is a little bit of a mystery. It's also kind of the same with genetic algorithm. You can understand what is happening, but you're not going to see each one of those numbers change, how it changes. And this is why a lot of game developers have shied away from using adaptive artificial intelligence. But it is nice that some have used this type of idea. Two different games, Colin McRae, this was I think it was number 2, was a racing game. They used neural networks to train how the artificial intelligence would navigate the track. In a very similar method to the old car experiment of the late 80s and early 90s. But they used a process called offline training, which is that we have, before the player ever plays the game, we train the neural network, and that is the final AI for the cars that are driving. It's done before any user has given input. And so it was given a little bit of help by seeing how the testers of the game played each track. And they were able to get a minimum distance line for each track based on how the testers were driving each track. They then used that as the basis of the error function for the neural network. And they did that for each track in the game. This led to a very good AI that was able to both stay out of the way of the player once they were being aggressive and take the shortest route around the track. Black and White used a process of online training. They didn't use a full neural network training system. They used positive and negative reinforcement, but the underlying AI in it used a neural network structure. You remember in Black and White, you had a monster that was, you gave it positive and negative reinforcement, and it would do things in this world. It would be a big, cuddly, giant teddy bear, or be a city-destroying monster. And you could train it to be that. And the way it worked is the weights on the neural network would gradually move up or down based on the positive or negative reinforcement that you gave it. Not a full neural network, but it was also much earlier when computing. We didn't have the same computing power that we have now. There we go. So these are a handful of the resources that I used in this talk. One is a book, one is a paper, and one is the backpropagation algorithm. So you guys give me your contact information, I'll make sure you get these slides. You can go look at this and see what you can make out of it. Right now, I am going to shift to Unity, and we are going to look at some code. Sure. And scene. All right. So, what I've done for this scene is I've created a neural network. I've created a series of agents that use neural networks. They don't really do anything except output numbers because this is just a demonstration. But those numbers can be used for figuring out an artificial intelligence's behavior structure. It's an interesting application for this. I have trained it based on a genetic algorithm because I don't have any data for anything that's really going on. Not in this case. So what we'll see, I'm going to play it, and in the console, no, I like to call them out. What you can see is I've created 400 agents. Each one of them has a neural network associated with them. And I will have them in code. Because I took all of my debug statements out so that I can see how well it performs. I guess over all of that. I've got 400 neural networks being trained about every 1/10 of a second. You can see that this is MacBook Pro, I forget which version, but I've got 16 gigabytes of RAM. It's i7. So that kind of lets you know in Unity, having 400 neural networks being trained every 1/10 of a second, I'm getting between 70 and 80 frames a second with nothing else going on. That's still a lot of room to be able to put your art and everything else that's going into the game. Here we go. So I've got my starter function. It is making all of my individuals, they, on their awake function. There we go. They, on their awake function, are immediately being told to assign a new neural network. So we are setting up our genes for the genetic algorithm. And those genes are being put into the neural network structure. So that when the genetic algorithm gives me new values for weights, those weights go in, and they are the weights for the neural network. Guess this will be clearer now that I have debug statements. There we go. So here is what my neural network looks like. You can see this is a series of 2 matrices because I'm working with a 2 by 3 by 2 neural network where it has 2 inputs, 3 hidden units, and 2 outputs. And so if we, can you guys see that? Okay, should I make this, that's not going to increase the font size. So if we, I'm going to go back real quick. So between these hidden units, what we can see is for this one we have 3 weights going out of it. So 1, 2, 3, and then 1, 2, 3. That makes the matrix here. So that we have 1, 2, 3 for the first input unit, and 1, 2, 3 for the second input unit. And those are the weights that are going into each of these nodes. And then here you can see that each one of these, because there are 2 to the next, I have a series of 3 2-unit arrays, which is exactly what I have here. So those would be the value of the weights, and in this case I've given a fake input, 1, 1, and here is the output that it gave me. So that would be 1 and 1 went in there and there. It did what it does, and when it got to here, it gave me this output. I can use that output to match this to some kind of behavior. I can use it to complete a pattern that the user has been doing. Say if we did a rock, paper, scissors type of game. If I saw that the player was repeatedly doing rock, 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 scissor, rock, 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 scissor, I could see that, complete the pattern, and do the appropriate thing at the appropriate time. Yes?
What's the range of the outputs?
Whatever you want. The question was, what is the range of the outputs? So it's whatever a float will contain, whatever an integer will contain. So you guys understand the structure and the weights? Awesome. So let's look at what a perceptron is. So in this, I've simply got a perceptron with an activation function. You can see I have my delegate here, and I've got a function for summing up all of the inputs that come in and the weights that go with them. So it simply multiplies the input by the weights and sums them together and then invokes my activation function. I have my activation functions listed in the network. There we go. You can see I've got my linear, I've got my step, I've got the ramp. And did you guys have any questions about the sigmoid or the Gaussian? No? Awesome. So there's those two. So when I make my neural network, I have a integer array that comes in that in this case is 2, 3, 2, and it is what creates the structure of my neural network. I use this to create my weights. Since this is a matrix, I don't need the same length. I need the information that is between your input layer, and in this case, the first hidden layer. And then again, the information that is between the first hidden layer and the output. So I need one less than the length of my structures. We are going to turn those into matrices, which I've made custom classes for because Unity's matrix 4x4 just wouldn't cut it. And for this, I'm simply assigning a random value to those weights, and then putting them in the weights for this neural network. And then we also need to create the perceptrons or the activation functions for them to interpret the inputs and the weights. And that's simply making an array of new perceptrons. So when this is if I already have a neural network in existence and I simply want to modify the weights or the structure. So here is the calculation function. Excuse me. So we're going to get an output that is based on the size of the final perceptron size, which is my structure is the final value in my structure array. We will go through with my inputs and the outputs equals the calculation of each perceptron based on its input. And that is so any questions on this? You guys getting neural networks in a gist? So that is basically it. Having a perceptron and summing up all of the weights and having an activation function for each perceptron will get you an output if you have your weights. Do you guys want to go a little bit deeper and see what a genetic algorithm is?
Yes.
Do it. All right. We have lots of time. So, for this, for the genetic algorithms, we have populations and individuals. An individual exists within a population. So here's what an individual is. I simply really made up of these variables, and that's about it. We have genes that are made of floats, and I've given minimum and maximum values that those can be the same of integers. We can have booleans. This would be the population this individual is associated with, and fitness is a measure of how well this individual is solving the problem. And that's really it. I've got a function to randomize whenever I want and to make new ones. Similar deal for population. Honestly, don't think these are used anymore. We have an array of individuals. I'm keeping an average fitness, yes.
How do you determine fitness for an individual?
So fitness is determined by whatever function you want to give it. In this case, where did it go? There we go. So in this case, I have this. What it was originally supposed to be doing was simply taking an average of all of the values, and that was the measure of the fitness. If it was higher up, it got a higher value. If it was lower down, it got a lower value, and just normalizing it. In this case, that's all it is. I put in a special stipulation because my integer size, which in this case would have gone to the structure of the neural network, but I didn't finish implementing it, had some bugs. I was like, well, can't have bugs in a presentation. But the idea is that you could use this part of the genetic algorithm to change the structure of the neural network. And since I set it so that the minimum and maximum are the same number, I was dividing by 0. So I've just got an if statement here. So if you're 0, just divide by 1. Yes?
So in terms of handling your data or your fitness algorithm in order to make sure that you can find out if your algorithm is working, how much did you have to mess with the random generator for Unity? Because when I was working on a project for my AI class, the random generator will always produce almost the exact same results each time. So it made it kind of difficult to get good random readings and actually see the algorithm doing its thing.
You're using random value?
Actually, I was in XNA using their regular random generator, so I was wondering if that was still a problem within Unity.
Sorry, he asked about Unity's random number generator, whether it was really producing enough randomness.
Was it enough randomness or any randomness?
That's Neo.
Yeah.
Did you see the random
Kinda, like to a certain degree, I was using floats, so to a certain degree in decimal numbers I was getting randomness, but not for any sort of good whole numbers. It was kind of weird.
Were you seeding it with like time value or something?
Yeah, I was doing everything, and it still wasn't.
You said you were using XNA?
Yes.
I'm not as familiar with XNA, sorry. With Unity, I've never had a problem with random.value or random.range. Just you have to keep in mind that with random.range, it's overloaded so that if you use floats, they are inclusive. The maximal is inclusive. If you use integers, it's exclusive. And that kind of makes sense if you're going to use an integer for an array. You don't want the last number to be the same as the length. So yeah, I've never really had any issues of Unity's random number generator. Did I answer your question about the fitness?
Yeah.
Because it's really any function that you want it to be. And however you decide this population is a good population. A real world example is I did a Fable type project where in Fable you had melee, ranged, and magic. And I set this up so that it was kind of a Rochambeau system, one kind of beat the other. With that, my fitness for the AI, based on what type they were using, was a little bit about how much damage they inflicted. Since they were all intended to die, I didn't measure how much health they lost. But what I did measure was how long they stayed on the battlefield. So that was some measure of how well they were surviving. I used that to figure out the fitness function for a genetic algorithm.
So, when you started doing that, did you run into a problem of like ones that happened to survive in a certain class, and there was and unless like there was a stronger weight of a certain type on this side, and they got defeated more quickly by all of them on this side. Like if this side was say range beat failing, this side started to get more melee, and then all of a sudden the entire population's fitness just sort of takes a nose down.
So he asked about if during the genetic algorithm process, if you started to get one population too fit and another population with very little fitness, would the side with very little fitness continue? And the answer is no. That's part of how a genetic algorithm works. So let's get into that.
Would you end up losing some of the benefits of diversity?
That's a good question. I'll get into that.
What? In real life, like body left papers, it's in a store, because you actually see the benefits to.
Do you have like a window to stop randomizing and just keep a certain or get a minimum number of certain
So you guys are asking about diversity and low fitness, and these are actually very strong debates that happen in the academic community about genetic algorithms. So you guys are hitting on very interesting stuff. There's lots of debate, lots of research going into how do we minimize diversity or maximize diversity, how do we minimize low-fit individuals. These are hot topics.
I guess it's always capped the low end, so
let's get into how exactly a genetic algorithm works, since we're going here. Genetic algorithm works by having a population of individuals. Those individuals are ranked on their status within the population based on the fitness function. And what we do is when we iterate through a generation, we select certain individuals for breeding. We pair them up. We have them create new children. Those children are then mutated just a little bit, and then they are reinserted into the population. Sometimes the old population is completely wiped out. Sometimes we only replace the poor individuals in the population with the best individuals of the children. There's a lot of leeway in how that happens, but the general idea is it's very similar to the way evolution works in nature. That is the general out there. So we go through there we go. So we go through parent selection. We have crossover of the genes of the parents to create children. We mutate the children, we replace them, and then we reevaluate their fitness. And we do this several times. Traditionally, we do this several times until we create a correct solution, or a pretty correct solution. What I did some of my research on in using genetic algorithms for video games was not to do so many iterations that you get a correct solution. Simply play it out as if it were nature. And the idea behind that was if we were in, say, an MMO, and we had a spawn point that was running on a genetic algorithm, you never want the individuals to become best. You want them to get a little bit better at competing against a certain class type. But because class types are running through the same area over and over and over, they're only going to be good against the last class type that came through. And so everybody else, it's a little bit easier for them. For the one, it's hard, but that's continually changing. So you can come, if you're one class and you come to that spawn point and it's hard to beat those minions there, you go away for a little bit, come back, and it'll be easy, or easier. So the population was continually evolving to fit the last group that was there. That was done by doing only a small number of iterations in this cycle, and then stopping and having those people respawn, and then when they die again, then do this just a few iterations, and that kept it balanced. So how do we select parents? My favorite method is permanent selection. It's really simple, low calculation. You just compare fitnesses. There had been lots of research into two different types using ranking and proportionality of the fitnesses. Mixed results. There's pros and cons for both. There's still pros and cons for tournaments. The big pro is that it's cheap on computation. It is usually not bad. And it also maintains a little bit of diversity. Because every once in a while you're going to get, in this case, 4 individuals that are competing in a little tournament bracket. And every once in a while you'll get 4 bad guys. It just happens, and so sometimes those bad guys do contain good genetic material, they're just overall bad. They're just good at one little part. That's basically it. We compare the fitnesses of them. Whoever has the highest fitness of this tournament goes on for breeding. So then, crossover. So, there are different ways of manipulating the genes of individuals, between 2 individuals, to create a child. The easiest way is simple recombination. If we have an array of values, we have two that are being compared, and we simply go through each index and we decide on a random number whether or not to switch them, that's all simple recombination is. There are other different variances. We've got one-point crossover where we take one index and everything before that index we leave alone, everything after that index we switch. And we produce two children based on that. One that was more so associated with parent A and one that was more so associated with parent B in a general sense. And after we have created two new individuals, we will mutate them. And so with mutation, this happens naturally in biology. It's typically a small change in the genetic structure, and that's really what we're trying to get here. It's you end up being just a little bit taller than your parents, or your red hair is a slightly different red. It's these ideas that we have a very small change that then result in getting new genetic material that your parents didn't have, and maybe you're getting better at the solution. Maybe not. Let's see, let's talk about creep. Creep is really the one that will get us to have very small changes. Let's say we have an integer. We have an integer of 2. Creep would only have plus plus or a minus minus, one or the other. You can do something very similar for floats. You can do it based on some type of distribution where you would only go up a little amount or down a little amount. Or you can have really dramatic mutations with random reset, where you take that index for that individual and you say, what are the minimum and maximum ranges? Let's pick a random number between those. Sometimes this is good, but usually the way I set this up is I have all these functions. We've got different probabilities that each function will happen for either crossover or mutation. So this one could be in there, but set to a low probability of firing. And then, yes?
What does a uniform and different do?
So, uniform, let's take a look.
Because it didn't look like there was an out here or anything, so it wasn't doing any of the list itself.
So right. So what we're taking is an individual that has a series of, it has an array of floats, an array of integers, an array of booleans to see what we're going to do with it. Uniform. So uniform is, it should be, let's see. All right, so there it is. These are all associative random resets, but uniform is for floating, random reset is for integers, and bit flips are for booleans. So creep here, this is for integers. This is the same idea, but for floats. And there's really nothing else but booleans that are either 1 or 0. So that's what they are. This is funny, all of the questions are going to be after the answer on this. But the question was, what is uniform and what is bit flip in the code that the audio also won't be able to see? After we have created new children, we will figure out some kind of replacement strategy. I mentioned a couple of those before, and then we'll reevaluate everybody in the population's fitness based on their fitness function. So with the process that I have here, this whole process is what is changing the weights of the neural network. So here I have some stopping criteria. As you can see, game we're done. In this case, we're looking for the fitness of the best individual to be almost perfect. I also, the points on stipulation that we want the average fitness of the population to be pretty good. But if those criteria are not met, we're going to iterate, and the iterate iterates the genetic algorithm for all of the individuals. It assigns the structure to be the integer values of the individual, whatever they were changed to in the weights. Because of what I've said, it stays at 3, so we have a 2, 3, 2 structure. And then after that, we assign the neural network of each agent to be the structure and the float weights. Excuse me. Of the individuals that existed in the genetic algorithm. And that is how, if we go back here, interesting. That's reporting the individual. So here are the float weights of the individual, and you can see, compared, you can look at the first 3. The weights for this part of the neural network are the exact same as the 3 first float values for the individual that's running through the neural network. They're being assigned to that. And this goes on throughout this, yes.
Do you know of any lightweight but actual game implementations that might be publicly available? Because I guess part of it is just seeing it in actual game situations.
So he asked about an example of a game where you could actually see this process happening.
If you don't know,
No, that's great. I'm going to write it down so that it's in these notes, so that everyone, when they get this, can see it. So Nero is a game that, as that says, uses a genetic algorithm to train the artificial neural networks of soldiers. So that you're given a little sandbox that you can put all kinds of different obstacles and enemies in, and you begin placing soldiers, and they begin doing the things. At first they're very, very stupid. But as time goes on with the training, they get better at performing whatever task that you have trained them for. And then you can use that to then go into, I guess, missions and have them perform. So if you say you have trained this tactic, this is some kind of split and surround tactic. They will get good at that, then when you go into a mission, you can say, perform my split and surround tactic. And they have been trained to do it, and they can do it. And it's very interesting to see individuals will begin doing the right thing, and then gradually all of the individuals in the group will begin doing the right thing, and then working together to do it. So that's a very, they have their own paper, they've got a game. The paper walks through how the game process works. I don't know if it's lightweight, but it is definitely a concrete example